In this video, we discuss symmetric matrices. A matrix A is symmetric if A equals its transpose, or equivalently, if the Aij entry equals the Aj entry for all I and j. So matrix A is symmetric if A equals A transpose. Example, the matrix, call it A, 1, 2, 2, 3, is symmetric. In this case, the reason is because the transpose of A, when you switch 2 and 2, that's the same as A. Another example, let's try 3 by 3 matrix this time. One, 5, 7, 3, 5, 3, 2, 7, 2, -5 is symmetric as well. If we call this matrix B, its transpose is equal to B, because you're switching 5 and 5, you're switching 7 and 7, and you're switching 2 and 2 when you find the transpose, and that's just identical to the original matrix. First, a fact. In order for a matrix to be symmetric, it has to be a square matrix. Let's look at a simple proof of that. Suppose it were not the case that symmetric matrices are square. Then we would have an instance of an m by n symmetric matrix where m is not equal to n. By definition of transpose, A transpose has to be an n by n matrix. Consequently, we would have two equal matrices, in this case A and A transpose, which do not have the same number of rows. This contradicts our definition of matrix equality. Here is a question. If A and B are symmetric matrices, such that their product AB is defined, is it the case that AB equals BA? The answer is negative. It is not true that if you have two symmetric matrices, A and B, that they commute. So unfortunately, the answer is no. To see this, let's consider the following example. Let A be the matrix, first row 1, 2, second row 2, 3. And let B be the matrix, first row 4, 5, second row 5, 6. If we multiply A times B, what do we get? Let's do that right now. 1 times 4 is 4, plus 2 times 5 is 10. 4 plus 10 is 14. 1 times 5 is 5 plus 2 times 6 is 12. When you add them, 5 plus 12, you obtain 17. 2 times 4 is 8 plus 3 times 5 is 15. 8 plus 15 is 23. 2 times 5 is 10 plus 3 times 6 is 18. So you get 10 plus 18, which is 28. Now let's do the reverse multiplication. B times A. 4 times 1 plus 5 times 2 is 14. 4 times 2 is 8 plus 5 times 3 is 15. 8 plus 15 is 23. 5 times 1 is 5 plus 6 times 2 is 12. 5 plus 12 is 17. And 5 times 2 is 10 plus 6 times 3 is 18. That totals 28. Observe that AB and BA are distinct. They are not equal to each other. Now, in this example, do make the following observation that if we compare these two results, you realize that the AB and BA are simply transposes of each other. So observe that in our example, AB equals the transpose of BA. Now, here is an interesting question. Could this be a general property? Okay, another question. If A and B are symmetric matrices such that the product AB is defined, is AB also symmetric? Well, let's take a look at our previous example. Here we had an example of two symmetric matrices. We multiplied them and observed that the result was not symmetric. So we will have to answer that's not true. That's not the case. Okay, so here is a summary. If S is the set of all n by n symmetric matrices, where the n here is a positive integer greater than 1, from our examples we see the following. The structure S multiplication of matrices is not commutative. The structure S with multiplication of matrices is not closed either. Okay. We do have a special property satisfied by symmetric matrices, and that is the following. If A is a symmetric matrix, so is its square. Let's prove that. So let's begin with the hypothesis that A is an n by n matrix that is symmetric. And let A squared be the matrix C. What we want to show is that in the matrix C, the ij entry and the ji entry are equal for all I different than j. That, of course, is the definition of C being symmetric. Okay, so let's work this out. Let's work out Cij. So what is Cij? Well, we know that it has to be the dot product of the ith row of A and the jth column of A. when you calculate it, you get AI1, A1J, plus AI2, A2J, plus and so on up until AIN, ANJ. Okay. We would also like to compute CJI. So let's do that now. CJI is the dot product of the jth row of A and the ith column of A. So AJ1, AJ2, and so on, AJN, dotted with the ith column of A, so A1I, so the ith column of A, so A1I, A2I, dot, 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 A and I. Now, let's work this out, compute it out. So AJ1, A1I, AJ1, A1I, plus AJ2, A2I, plus dot, 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 plus the last one, AJN, ANI. Now, if we are to compare them right now, it does not appear that they are the same results. Here is CIJ, and there is CJI. But let's remember that A, by hypothesis, our matrix A is symmetric. A is a symmetric matrix. So that allows you to realize that AI1 equals to, that allows you to realize that AJ1 is the same as A1J, A1I is the same as AI1, plus we treat every term in a similar fashion. So here I'm going to get A2J, AI2, plus dot, 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 and then in the last term I have ANJ, AIN. Now we're a little bit closer. It's just a matter of one last detail. In order to make a perfect match, we would like to be able to commute each of these products. And that, of course, happens because each of these entries are real numbers, or even if they are complex numbers. The commutative property applies. So we end up with AI1, A1J, plus AI2, A2J, plus and so on, plus AJN, ANI. And now we have concluded that CIJ equals CJI for all I in J. Okay, so our proof is complete. Okay, so here is an interesting question. This is a follow-up question. If A is an n by n symmetric matrix, with n greater than 1, is A cubed also symmetric? That's an interesting question to think about. Okay, now let's define diagonal matrices. A matrix A, an n by n matrix A, is diagonal if and only if it is symmetric and Aij is 0 for all I and j distinct. In other words, a diagonal matrix is a symmetric matrix whose entries are all zeros except those that are in the diagonal. So here are some instances. 2 by 2 diagonal matrices have this form. Everything of the diagonal are zeros. The diagonal are any generic entries. 3 by 3 diagonal matrices have this form. The diagonal entries are generic, but every non-diagonal entry is 0, etc. Okay, so here is a property. Let n be a positive integer. If A and B are diagonal matrices, then the product AB is also a diagonal matrix. Now let's look at a proof of this. So begin with the hypothesis that A and B are n by n diagonal matrices. We aim to show that the ij entry of this product, which we're calling C, is 0 for all I and j distinct. So what we need to do is we're going to find the entries themselves. So we're going to find the ij entry of C, Cij. So that's the dot product of the ith row of A and the jth column of B. But observe that every one of these entries is 0 except Aii, and every one of these entries is 0 except Bjj. So you end up with Cij equaling the dot product of 0, 0, 0, dot, 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 0, Aii, 0, 0, 0, 0, 0, and the column 0, 0, 0, 0, 0, Bjj, 0, 0, 0, 0. So the result is the following. You're multiplying 0 times 0 plus 0 times 0. At some point, you're multiplying Aii times 0 plus that. At some point, you're multiplying 0 times Bjj plus 0, 0, 0, which equals 0. This, of course, is under the presumption that I and j are distinct. In this case, we are assuming that I is less than j. Okay, so that's our proof. This has shown that the matrix C has all non-diagonal entries equal to 0. So that means C is diagonal. Okay, so another property. If A and B are diagonal matrices, are diagonal n by n matrices, then AB equals to BA. Well, we already know that the product AB is a diagonal matrix. BA is a diagonal matrix. The only thing that you need to be concerned about is the generic entry in a diagonal of AB the same as the generic entry in the product BA. Okay, here is a summary. If D is the set of all n by n diagonal matrices, here n is a positive integer, then The structure D under matrix multiplication is closed, meaning that when you multiply two diagonal matrices, n by n diagonal matrices, the result is also an n by n diagonal matrix. So that property is satisfied because of our first property, of diagonal matrices. Second says that the structure D under multiplication of matrices is commutative. That is also the case because of our second property of diagonal matrices. Okay, so that concludes our presentation on symmetric matrices. Thank you for watching.